little bit nervous today because we're going to talk about some neuroanatomy. Okay, what I want to do is talk about reflexes, and it's neuro, there's no getting away from that. But it's also wiring. So what I want to do is, I want to talk about a couple of different types of reflex, you know, like the patellar tendon reflex, well not that reflex specifically, but muscle stretch reflexes. What are they called? Myotatic reflexes. And then I want to also talk about like the pain, the withdrawal reflexes, or also get called the flexor reflexes, where you know you put your hand on something sharp, yeah, and you've pulled away from it, you've pulled that limb into your body, and it's super fast. So reflexes have evolved as a survival mechanism, as a safety mechanism, and they don't involve the higher centers, they don't involve the brain, they are localized within the spinal cord. So that's what we're going to talk about, is that circuit diagram for those two different types of reflexes. Got my box of pipe cleaners, so we're going to build these up with pipe cleaners, and the aim is to get some core concepts and ideas across, and then we'll reinforce our understanding of an upper motor neuron and a lower motor neuron, and we'll talk about what happens to those reflexes if you cut the spinal cord versus if you cut the peripheral nerve. That was a long introduction. Suggest it's going to be a long video. Okay then, if we think about the stretch reflex first, as I said, also called the myotatic reflex, sometimes also called the monosynaptic reflex. The reason I want to start with this is because it's the simplest idea. Monosynaptic. A synapse is a connection between two neurons. Monosynaptic suggests that there is only one, and that is the case. How am I going to do this? So, right, so quadriceps muscle, knee joint, patellar tendon. The quadriceps muscle passes over the patella, inserts into the tibia. Now, it's very helpful to have reflexes, so autonomic processes, automatic processes in which muscles can detect their own stretch and change their contraction relative to it. Helps you with your posture and balance and that sort of thing, right? Because you've got muscles that are contracting, muscles that have posture all the time. You don't want your brain involved in all of that. If you can automate as much as possible, much of it as possible, brilliant. So on the one hand, that's why some of these reflexes exist. On the other hand, we use these reflexes clinically to help us better understand what's going on in a patient. All right, back to what I was talking about. So the patellar tendon reflex is a quite good one, right? So I've got this leg over my other knee, there's a little bit of stretch in there. Now, if I rapidly stretch the tendon, the muscle reflexively contracts, right? And to prove I'm not mucking about, you can do this on yourself. So, what's happening when I do that then? Right, well, I'm stretching the muscle, so in the case of this particular reflex, although this is going to be similar for most other reflexes, this is the muscle I was on about. So that was the tendon. I was stretching that tendon, which meant that sensory information from the stretch receptors was traveling back with the femoral nerve to the spinal cord, and then somehow that triggered the motor nerve fibers, turns out in the same nerve here, the femoral nerve that are running into the quadriceps muscle, to contract. So in that case, the femoral nerve is the peripheral nerve, and it has afferent fibers, so sensory fibers running into the spinal cord, and efferent fibers, or motor fibers, running out of the spinal cord into the muscle. All right, so that would be our first two pipe cleaners. Just kind of, right? So how am I going to, if I have a bit of muscle, okay. Here's my spinal cord. They didn't hire me for my artistic abilities. This is dorsal, so towards the back. This is ventral. So this is the dorsal. This is grey matter here, right? This is the dorsal horn, which means all the sensory stuff goes in here. And this is the ventral horn, so all the motor stuff goes out here. Okay, so there's our muscle. The green fibres then, this will be the sensory bit, right? So the sensory bit, oh God, I wish I'd think these things through sometimes, you know. So, and this is like a single neuron. These neurons have got long axons. So there's not like lots of synapses along here. The neuronal cell body is in the dorsal root ganglion here, and it sends one process into the spinal cord and one process out to the sensory part of the muscle. So this is the afferent part of the reflex. And then the motor nerve just does that. So the motor fibers, this would be the lower motor neuron. These would be the afferent fibers, the motor fibers. A motor neuron sending an axon out through the ventral horn into the muscle that will cause the muscle fibers to contract, right? And what happens in the spinal cord is that in the grey matter, there is a connection between the two, and that's it. That is the single synapse of the monosynaptic reflex. So muscle gets stretched, sensory information comes in, triggers that, causes that muscle to contract, muscle gets shorter, you kick your foot in the air. So that is your super simple reflex. Sensory stuff in, triggers this motor neuron, and this neuron, remember, can be triggered in other ways. This isn't the only way it gets triggered. There are multiple connections that neurons have with other neurons to make different things happen. This is just one example of how this neuron can be triggered to cause that muscle to contract. So that is the simplest form of reflex. And we can build on that, because there's a little bit more to it, in that if you think about it, right, if this muscle is going to contract to extend the knee, then the muscles on the opposite side have got to relax to let you extend the knee. These are the antagonistic muscles. And if you're going to have a reflex that causes this muscle to rapidly contract, it would be very safe and helpful if you could also reflexively tell these muscles to relax, so you're not having big muscles pulling against each other, right? So the reflex also does that. So there is a little bit more to the story. Well, let's have a hamstring then. Oh, bum bum, bum bum. So the hamstring muscle has got to relax. We've got our quadriceps muscle. That same loop still works. We'll add a hamstring muscle. Now our sensory nerve is also going to, I'm going to need a short nerve, a pair of scissors, is also going to synapse with a short interconnecting inhibitory nerve. These connections will be inside the grey matter of the spinal cord. That's what the grey matter is about. It's about connections. There's no myelin in there. The white matter of the spinal cord, they are myelinated neurons. They're travelling somewhere. The myelin makes those action potentials travel more quickly. Right, so we have an interneuron, an interconnecting neuron, and then we're going to need another motor neuron that goes out to the hamstring muscle. Okay, let's wire this up. This is actually going to have another connection. Why do I do this to myself? Okay, so this sensory neuron carrying that stretch information is going to send off a second process that is going to synapse with what gets called an inhibitory interneuron. And this inhibitory interneuron is then going to connect to the neuron. This is a motor neuron. So this is the hamstring muscle. This is the one we want to relax. This is the quadriceps muscle, the one that needs to contract. So the sensory information comes in from the tendon, carrying stretch information back to the spinal cord. There's that synaptic direct link to this motor neuron that's going to cause that muscle to contract. And then it also sends out a process that synapses with this inhibitory interneuron, which triggers this motor neuron here, not to tell this muscle to contract, but to tell it to relax. So this is about inhibition. So that's a bit more. All right, so that's how tendon reflexes work. It's a reflex contained within the spinal cord. The brain doesn't have to get involved for that to happen. However, the brain does send down neurons that can modulate that activity, and we'll come on to that towards the end. All right, there's the tendon stretch reflex then, and we'll probably talk about the individual anatomy of tendon reflexes at some point in the future. But the other reflex that's fun that we all tend to learn about is, as I said, is the withdrawal reflex. When you put your hand on something hot or you step on something sharp and you immediately, and we're talking milliseconds are important here, pull your hand away from that hot surface to reduce the amount of injury to your hand, your skin, so you don't cook yourself. How does that work? It's very, very similar, except of course it's using receptors in the skin. So we're not just working from muscle to muscle, but we have receptors in the skin forming reflex arcs with muscles in the limb that then draw that limb away from the hot stimulus because it's pulling it back in towards your body, basically, which is why it gets called a reflex, a flexor reflex. Although if you look at them, then not all flexor reflexes, so a withdrawal reflex is quite a good term for it. Okay, how does that work? What can I use for skin? I'll use my skin for skin. Is that going to work? We'll use a bit of muscle for muscle, but here we're talking about the upper limb. We're using the upper limb as an example. So if I put my hand on a hot surface, then cutaneous nerves, sensory nerves will carry, that'll be the sensory limb, the afferent limb, carrying that sensory information back to the spinal cord. We'll use green again, shall we? So there's the spinal cord, there's my hand. So skin, sensory information is going from the skin into the spinal cord. Now here, there will be an interneuron. This isn't inhibitory, this is just an interneuron that is then going to connect to the motor neuron, which we should call a lower motor neuron, that will run to the muscle. So this is biceps, for example. So then when my skin feels pain, that sensory information goes into the spinal cord, doesn't bother going up to the brain and back down again. Synapses with this connecting this interneuron, again in the grey matter, to this motor neuron. It tells that motor neuron to fire, which then runs to the muscle, which then tells that muscle to contract. So again, a reflex arc. The brain is not involved, but the brain does send down fibres that can act upon that reflex and, dampen it a little bit. As usual, there's more to the story, a little bit more, because we've got to do the same thing again, haven't we? If we're going to contract biceps, then we want to relax triceps, because if you try and contract biceps and triceps at the same time, nothing happens. Your arm doesn't move. So if we get another, what we're going to need is another interneuron. Bump. So this is a little bit simplistic, but okay. All right, same again then. So skin on my hand. This is the sensory neuron. I've touched something hot. That pain is being transmitted by this afferent neuron, this sensory neuron, in through the dorsal horn of the spinal cord, and it synapses with this interneuron. And this interneuron sends an axon out to this motor neuron telling biceps to contract, to pull my hand away. But this interneuron, this inhibitory interneuron synapses with this lower motor neuron and inhibits the contraction of the muscles of triceps, which means that biceps can contract unimpeded by the contraction of triceps. So you touch the hot thing, the flexor muscle can contract, the antagonistic muscle doesn't oppose that contraction. You take your hand off, it's super. Because you know what it's like, right? You burn yourself. you know, you burn yourself, it's like, yeah, and you've already done damage to yourself in that tiny instant that you were cooking yourself. So it really is important that you take your hand away from that source of heat very quickly. It's the same if you step on something sharp. So that is, I mean, it's a little bit of a simplistic view, but it's not wrong. That idea of a neuron extending from one point all the way down to another point, and the fact that we actually, okay, we've got bundles of neurons, so we've got thousands and thousands of millions of neurons running alongside each other, but that wiring of one neuron meeting another neuron, and having a 3-neuron chain or a 2-neuron chain, that's an important idea. And that really helps you understand how all this works. There is more complexity to all of this. For example, those muscle fibers will be innervated from different levels of the spinal cord. So in fact, those inhibitory neurons I showed you could be on 2 different levels of the spinal cord. And you can get reflex arcs, so inhibitory reflex arcs, or you can get reflex arcs crossing over to the other side of the spinal cord, so to the other side of the body. So that if you do step on something sharp, you reflexively maintain your balance because the muscles on the other side of your body adapt, so you don't just step on something sharp and fall over, which could put you into even worse peril. It's pretty amazing stuff. All right. Now, I said I'd talk about upper motor neurons and lower motor neurons and how we use these reflexes clinically. Right, get your thinking caps on then. Okay, we've been talking about the lower motor neuron. Those are the neurons that come out of the spinal cord and run out to the muscle. So peripheral nerves, the musculocutaneous nerve, ulnar nerve, radial nerve, median nerve, whatever you like, those peripheral nerves are carrying lower motor neurons. So where are the upper motor neurons? The upper motor neurons are inside the central nervous system. They're running between the cerebral hemispheres and they're running down the spinal cord. And the upper motor neuron will meet the lower motor neuron, and that's how you make your muscles move. Okay, so that means that we can use reflexes to test these things. Think about reflexes. So if you're testing the reflexes in the body, the central nervous system can dampen, so it's generally described that those upper motor neurons can dampen those reflex arcs to give us the reflex that we saw when we tapped my patellar tendon, right? So the upper motor neuron dampens that reflex arc. If the spinal cord is severed, what would happen to that reflex then? So straight after a spinal cord injury, there's going to be spinal shock. The reflexes will probably be absent. There will be areflexia, right? You won't be able to elicit reflexes, but that's because of spinal shock. After time, when the spinal cord has recovered a little bit, what do you think will happen to those reflexes if the upper motor neurons have been severed? The reflexes will be strong, they'll be hyper-reflexive. The reflexes will be faster than normal, right? They'll be more powerful because they won't be dampened by the upper motor neurons, which is why that tends to get called an upper motor neuron lesion or an upper motor neuron deficit, because the upper motor neurons can be injured by things other than other than by severing the spinal cord. They could be damaged by a stroke. You know, the damage to the brain can damage the upper motor neurons because they're up in the brain as well. Okay, so the lower motor neurons are in the peripheral nerve. What will happen to the reflex if you sever the peripheral nerve? So the musculocutaneous, all right, we were talking about that ain't going to work. We were talking about the patellar tendon reflex. The femoral nerve is carrying the afferent and the efferent fibers, that is the sensory and the motor fibers of that reflex. So if the femoral nerve is cut, what will happen to the patellar tendon reflex? Do you think? There won't be a reflex. It won't be possible because you will not be able to For one, you won't be able to take that sensory information from the tendon back to the spinal cord, but for another, you won't be able to send motor information to the muscle, causing the muscle to contract. So that would be called a lower motor neuron deficit. So when the lower motor neuron is injured, when the peripheral nerve is damaged, the reflex is likely, well, if it's completely severed, the reflex will be gone, areflexive. All right, now that's your starting point. Those concepts, if you understand that wiring, that concept, and you understand upper motor neuron, lower motor neuron anatomy, and you understand how the central nervous system can have an effect over those reflex arcs, you're there, you're golden. You can build loads of reflex complexity on top of that, other types of reflexes, bits and bobs, and clinical understanding, all right? But I wanted to just try to explain it as clearly as I could. I don't know if that was clear, to give you a fighting chance. But reflexes are really cool. I mean, that anatomy just shows you how cool neuroanatomy is, really. When you start to understand it, it's just amazing. And you can imagine how that's evolved through the billions of years as well. Right, anyway, stop chattering, Sam, but yeah, see you next week. We'll look at the individual reflexes in some time in the future.